Hi, and welcome back to ENAE 788M, Hands-on Autonomous Related Robotics. So let's move on from our essential and fundamental matrix to more 3D geometric version of how do we solve the problem of structure from motion. So recalling the essential matrix from the last slide. So we know that my essential matrix is my camera matrix transpose times fundamental matrix times camera matrix. And we know that in E we have normalized image coordinates rather than pixel coordinates that we discussed in the class as well. And the essential matrix E basically is a 3x3 matrix, which is corresponding the feature points between image 1 and image 2. And it also follows the pinhole camera model, unlike your fundamental matrix. Right? So how do we estimate the pose from the essential matrix? So what is a camera pose? First of all, camera pose has a 6 degree of freedom, which has 3 in rotation and 3 in translation. So roll, pitch, yaw, and XYZ. So the way you estimate pose is first you do, like always, you do SVD, K transpose, SVD of K transpose F times K. And now you will have U sigma V transpose. This is the standard SVD. Here U and V are the orthogonal 3x3 matrices, and sigma is a 3x3 diagonal matrix. And for this solution, like if you want to solve this solution, you will have 4 possible solution camera pose estimation, right? So you can call that C1 R1, C2 R2, C3 R3, and C4 R4, but only one would be correct. Like out of these 4 sets, only one set is a correct pair of my translation and rotation. So C represent XYZ or translation, and R represent my roll, pitch, yaw, rotation. Okay, and R is a rotation matrix, is belong to an SO3. Okay. So one more thing I want to add is that not every arbitrary 3x3 matrix can be an essential matrix for a pair of images. So this is our standard projection equation, and just writing that, I can say that my translation has like these 4 values, and my rotation has these 4 values, which of 3 pair is incorrect and only 1 pair is correct. So why do you think we are having 4 values? Because 2 of these values are one of these value is like the mirror image. Let's say your features pointing somewhere up, right? One of the pair is literally a mirror image pointing downwards like this. Okay, the other thing is this is one set, right? One is pointing towards on the top right corner, let's say, which is correct, for example, and the other one, which is the mirror image, which is pointing somewhere in the bottom right direction, right? And the other 2 pair are actually the mirror image of these 2. So we want to eliminate these 3 incorrect pairs, right? So let's see how we can do it. So you guys must have heard of triangulation. It's used in GPS localization, has been using from a long time. So it says that if you have, like, let's say A and B are 2 cameras, right? And L is the length between these 2, right? So I can estimate D if both A and B are seeing the same common point, which is the ship in this case. Okay, so you can simply, by traditional geometry, you can say that L equals D by tan alpha plus D by tan beta, and then you can just compute D equals L times sine alpha into sine beta by sine alpha plus beta, right? So how do we do triangulation when it comes to computer vision? So the problem basically is, given a pair of C1 R1 and C2 R2 and the correspondence between X1 and X2, basically feature matching, we want to triangulate 3D points using linear least square. And there's a thing called chirality condition, which is basically you're removing the disambiguous output. So you were having the 4 outputs. So how do we remove 3 of them? It's called chirality condition. This is based on my I'm computing basically X minus C, and if it's greater than 0, I'm good. Not X minus C, my third row of X minus C. So let's see what R3 is the third row of my rotation matrix. C is a set of from my linear triangulation output. So this is my translation, and X is a set of 3D world points, which is X. C is a camera translation. So if this equation holds true, it's gonna be in one particular condition, and that's my correct value of my correct C and R pair. Okay, so basically we are doing triangulation to determine a point in 3D space. Okay. So how does the plot looks like? Let's talk about that. So we have 4 possible camera poses. We want to remove the disambiguity. So we have these 4 possible solutions. Let's say you see these 3 gray and 1 blue. Only the blue one is correct, and by the blue one you see this 3D world point which are computed in red. For the other one is computed is shown in blue. The third one is computed in black, and the fourth one is computed in green, right? So you can see that 2 of my pairs are actually the exact mirror image of the other 2 pairs, because that assumes that my image is behind the camera, which is invalid, right? So these are the disambiguity if you want to plot these things. Only one is correct, right? So all these pairs that you can see are well color coded, and only one is correct, right? So to remove that, you should get something like this, like literally deleting every other pair, and you should get the correct camera pose or the camera direction, and you will get the correct 3D world points. So now let's talk about a more non-linear triangulation, because our linear triangulation is not that robust. It assumes something about the scene, which assumes linearity about the scene, which is not going to happen in your real world. So let's see how we can go through the non-linear version of triangulation. Okay, so it's basically refining the camera poses, right? You have a good or fair estimate of camera poses using the linear version of triangulation. We are gonna use that and as the initializer, and then we're gonna refine these poses, right? So the idea is to minimize the reprojection error. What it is, we'll talk about it. So we are basically trying to minimize the Euclidean distance between my U1 and my reprojected point. So my point, it has some space, right? And I use the projection equation and get the 3D point, and then I project it back to something like to the same image plane, right? But these 2 points won't be at the same point, because there is some error when we use linear triangulation. So this Euclidean distance between these 2, we have to minimize, right? So we have to minimize for the left image and the other right image, right? So basically we are trying to minimize. This is the 3D Euclidean distance between the points and the reprojected points. And notice that this is for every camera index, and here P is my projected matrix, and PT has like a 3x3, right? So each row of the camera projection matrix. So why are we dividing with the third row is to normalize, okay? And the last thing to note is it's x tilde, this thing, is a homogeneous representation of my x that we talked about before. So this part is for the first image or the first view, and this is from the second view. So we want to add them, and we want to minimize this to refine my camera poses. Okay, so you can see the results between the linear version and non-linear version. So this is a top view from points that represents a building, right? So the red points, you can see it's much more farther away, and you can't see probably you can't see a straight line or something. But when we talk about the blue points, it's much more subtle, and the points are much closer, and it correctly represents 2 lines, and it also correctly represents these 2 angles being 90 degrees. So this is how your result should look like between your linear estimates of poses and non-linear estimates. Okay, next thing is perspective endpoints. So this is a very fundamental problem which says that, okay, I want to estimate the pose of a calibrated camera. When I say pose of the calibrated camera, it means my K matrix is known, right? So given a set of n 3D points in the world coordinate system, and you have the 2D projection, so you can say that you have the correspondence between capital X and small x from triangulation, right? And you can assume that my n is greater than 3, right? So you had n 3D points, right? Let's say you have one image, you have second image. You at least, if you have like these more than 3 world points, you can solve using least square, and you can find the pose of a well calibrated camera. Now if n equals 2, you can also solve that, but there's a catch that you should the feature orientation at these 2 points must be available in all frames. Okay, so once you estimate the camera pose, your camera pose will look something like this. So each triangle is basically your position and orientation of the each camera that you took an image from, right? So given a 2D 3D corresponding set and K, we are basically solving the least square problem, and we are estimating the camera pose. Okay, one more important thing to note here is that we are normalizing the 2D points by K. This is basically to isolate your position and rotation of your camera poses, right? So what you do is basically you do K inverse X, right? This is how you normalize, and then you use least square system, which basically is relating my 3D world coordinate system to 2D world coordinate system, so I can compute my actual translation. Okay, similarly for rotation of these, I can do SPD, the thing I did above, and I can say my rotation is equals UV transpose, right? Now if you have an correct estimation of R, you must have my determine R equals -1. Okay, but if you have incorrect, you have to negate this if something like this happens. Okay, also your estimate of camera pose is not always correct, right? There are, just like triangulation, there are some fundamental problems because they have a lot of outliers, right? So PnP is very prone to outliers. And one more thing, PnP, the n is representing the endpoint, so minimum, because you need 3. So there's a very fundamental algorithm called P3P, so you have 3 world points, and these are a little slow, if you want to call it, not that robust. So people have developed these algorithms. One of them is called unified PnP, and there's one called efficient PnP or ePnP. You can look at that if you want to. So coming back to the point, PnP is very prone to outliers, and like always, RANSAC to the rescue. So you want to make your pose estimate much more robust. So in this, you need a minimum of 6 3D to 2D correspondences. So from capital X to small x, you have to have at least 6 corresponding points, right? So again, how do you do this? How on what RANSAC is based on is by measuring my reprojection error that we also saw in the nonlinear triangulation, right? So let's see how the algorithm works, right? So you have in linear PnP, you had you're solving basically given my capital X, small x, and K, okay, and you have the correspondences between capital X and small x. You get the position and rotation of the camera, right? Now once you have that, you are measuring the projection error, and this is basically the selection criteria if you want or if you don't want these camera poses, right? Just traditional RANSAC. Okay, so this is what was there in my non-linear triangulation, right? So you can see, you can compare these two. These are both measuring the reprojection error, so it's kind of the same thing but for PnP. Okay, but there's another version called non-linear PnP, right? So linear PnP minimizes the algebraic error. but there's more to it. So my reprojection error is computed by measuring the error between measurement and the projected 3D points, right? Something like this that we saw. And we again, my x tilde is my homogeneous representation of x, right? And this is the same definition that we use for both, right? So although my representation in the quaternion space is much better to enforce orthogonally because I know that things are orthogonal, right? So when I'm doing this in rotation space rather than quaternion space, my results would be very much prone to error, right? But if I'm converting my rotation space and working in the quaternion space, I will have much better estimates. So I'm converting my rotations to quaternions and I should get something like this, the same equation, but I'm minimizing these rather than minimizing for C and R. I'm doing it for C and Q, where Q is a quaternion with the 4-dimensional, it's a 4-dimensional quaternion, right? So this minimization is highly nonlinear because of my quaternion parameterization, okay? And another point is that my initial guess is coming from the linear PnP to minimize the cost function. So same thing, like I do linear triangulation, then I use that estimates to solve for nonlinear triangulation because I want to start with a good estimate. Same thing here, I do linear PnP, which is okay, it's not bad, but it's a very good estimate, and I feed that estimate to my non-linear PnP to get a much robust pose. Okay. So in Python you can use scipy.optimize.least square or make it maybe scipy.optimize underscore least squares, the same thing. So these two algorithms are a little different, but they will do the job for you. Okay, so let's talk about bundle adjustment. Okay, so till now you have separately, so this is the Python, right? You do feature matching, you then compute fundamental matrix, then you are estimating essential matrix given camera calibration matrix and fundamental matrix, then you do, and then you are estimating pose from essential matrix, and followed by triangulation and chirality condition to remove the disambiguity. Then you do nonlinear triangulation for much better estimates. Then you do PnP to estimate the camera pose, and you do nonlinear PnP to refine these camera poses, right? So we are in triangulation, we are estimating the 3 world points. In triangulation, we are estimating the camera poses, but we are not doing everything together, right? So bundle adjustment is basically putting everything together from triangulation and PnP and everything of not just 2 images, but a series of images, let's say 10 images, 15 images, something like that, or even more, right? You want to put everything into one big giant optimizer and refine these camera poses and the 3 world points together as a whole. Okay, so your minimization problem looks something like this. So again, these are my reprojection error, and same thing for the second frame, right? So there's a thing called visibility matrix. What visibility matrix is, it's basically is a relationship between the camera and the point. So you can construct an I cross J binary matrix. Okay, so Vij, you can see here, right, is basically telling me that, okay, between frame I and frame J, is that feature point available in that particular frame? If it is, then the value is 1. If it's not, the value is 0. So between 2 particular frame, I will have a huge matrix just having zeros and ones. Okay, that's what visibility matrix is. And you have this minimization problem, and you're doing for every image. Okay, so we are trying to minimize C, Q, and X together. So this is for the camera, this is for the X set, which is the world points. So world points and the camera poses, minimization together, right? So you should have much more refined output, which should look something like this. So again, the problem with bundle adjustment is the number of parameters is huge. So if you are using a very, if you're using a non-optimized piece of software and if you're trying to optimize this, then let's say for 10 images it might take like 6 to 7 minutes, for example, which is insanely slow if you're working on quad rotors, right? So that's one drawback of using bundle adjustment. That's why people say that they can do SLAM on quad rotors, right? But the truth is the SLAM is inherently very heavy if you want to create a 3D structure of the scene on a moving quad rotor, and especially if you have a very small computer, because you can't carry the entire i7 PC on your drone, right? So this is the main problem that people talk about. They want to do SLAM and things like that, but we have to, if we are doing SLAM, we have to be very efficient about it, right? So it can take a few minutes, like we discussed, right? So this view that you're seeing is a sparse bundle adjustment, but you can also fill in these missing gaps by something called path distribution. So basically, if you know a point which corresponds in one image and the second image, right? Not just detecting the feature, but you basically assign a patch around it, and you're trying to match these patches, and then you basically project onto this 3D world way. So in Python, you can try PySBA, or there's a thing called large scale BA in SciPy. You can try these two. You don't have to write your own bundle adjustment if you want to implement this. That's fine, because this is a big optimizer, which is sort of okay. So this is the overview of how bundle adjustment works, right? You have a given data. You have basically what you want to do is, given data, given calibration matrix, you want to find my X, C, and R. So I want to find my 3D world points, camera translation, and camera rotation, right? So first step we did was feature matching. We did RANSAC for rejecting the outlier. Then we estimated the fundamental matrix. Then we estimated fundamental matrix for essential matrix. We estimated essential matrix from fundamental matrix using the calibration matrix, right? And then we estimated camera pose from my essential matrix, right? Then I did linear triangulation given my camera poses. So I checked for chirality condition, and I disambiguated the bad poses. So I have now C, R, right? Then I did my non-linear triangulation to get the 3D world points refined, right? Now this is the camera registration problem, where I basically using PnP and non-linear PnP, I'm getting my 3D world points, 3D camera poses, and then I'm putting everything into a big chunk of optimizer, which literally optimizes my C, R, and X together in which is called bundle adjustment. So that's it for today. This is the overview if you want to look at it. If you want to read more about how these things are derived, everything is available online if you want to go with that. And we'll talk about much more sophisticated graph approach version of structure for motion problem, and how we can make it quote unquote real time. So we'll talk about in the next class. That's it for now.